Section 1. Introduction. The transformer model has become a popular choice, especially for large language models, LLMs, and multimodal models. However, it has a significant drawback. Its computational complexity increases exponentially with the length of the input sequence. This makes it difficult to handle very long sequences, which are often required in LLMs. Despite this challenge, the idea of unlimited sequence length in LLMs has attracted a lot of interest, as it has many potential applications, such as extended conversations in various professional fields and handling a large number of tokens in multimodal modeling tasks. To overcome the computational complexity issue, a promising solution has been proposed: linear attention. This approach eliminates the softmax operation and takes advantage of the associativity property of matrix products, which significantly speeds up both training and inference processes. In simple terms, linear attention reduces the computational complexity from a square of the sequence length to the sequence length itself by using a technique known as the kernel trick to calculate the attention matrices. However, it's important to note that this reduction in complexity is theoretical and may not directly translate into a proportional improvement in computational efficiency in real-world applications. This is due to two main challenges. 1. The dominance of memory access on the GPU, which can affect the overall computation speed of attention, and 2. The need for cumulative summation in the linear attention kernel trick, which prevents it from reaching its theoretical training speed. To address these issues, we introduce Lightning Attention-2. This approach uses a divide and conquer strategy by separately handling the intra-block and inter-block components in the linear attention calculation. For the intra-blocks, we use the conventional attention computation mechanism, while for the interblocks, we use the linear attention kernel trick. We also use tiling techniques to fully leverage GPU hardware capabilities. As a result, Lightning Attention-2 can train LLMs with unlimited sequence length without extra cost, as its computational speed remains constant with increasing sequence length under fixed memory consumption. We evaluated Lightning Attention-2 across a range of sequence lengths to assess its accuracy and compare its computational speed and memory usage with FLASHATTENTION2 and Lightning Attention-1. Our results show that Lightning Attention-2 has a significant advantage in computational speed, thanks to its innovative intra-inter-separation strategy. It also has a smaller memory footprint than its counterparts without compromising performance. Linear transformer architectures replace the softmax attention mechanism with different approximations. The main idea is to use the kernel trick to speed up the attention matrix computation. Several methods have been proposed to replace the softmax operation. However, the practical computational efficiency of linear attention decreases significantly in causal attention scenarios, mainly due to the need for cumulative summation operations. The Flash Attention series focuses on system-level optimizations for efficient implementation of the standard attention operator on GPU platforms. It uses tiling strategies to minimize the volume of memory reads, writes between the GPU's high-bandwidth memory and on-chip SRAM. To address the slow computation issue for linear attention in the causal setting, Lightning Attention-1 uses the approach of FLASHATTENTION-2, which involves dividing the inputs into blocks, transferring them from slow memory to fast memory, and then computing the attention output with respect to these blocks. The final results are then accumulated. Although this method is more efficient than the PyTorch implementation, it does not take advantage of the computational characteristics inherent to linear attention, and the theoretical complexity remains a square of the sequence length times the dimension of the input. A common strategy to handle challenges related to length extrapolation involves the use of relative positional encoding techniques, which strategically direct attention towards neighboring tokens. Several methods have been proposed to enhance length extrapolation properties. However, these methods can only extend sequence length in fine-tuning or testing phases, while our method allows training models in long sequence lengths from scratch with no additional cost. Section Summary. The transformer architecture, widely used in large language models and multimodal models, faces challenges in modeling extremely long sequences due to its quadratic computational complexity. Linear attention, which eliminates the softmax operation and leverages the associativity property of matrix products, offers a promising solution by reducing the complexity from O(n) squared to O(n). However, practical implementation faces challenges related to memory access and the cumulative summation needed by the linear attention kernel trick. In this paper, Lightning Attention-2 is introduced to address these challenges by separately handling intra- and inter-block components, resulting in efficient training of language models with unlimited sequence length. Section 3.1 Preliminary. Let's start by revisiting the concept of linear attention and then introduce our proposed model, Lightning Attention-2. In the trans-normer model, the norm attention mechanism deviates from the traditional transformer structure by avoiding the computationally expensive softmax and scaling operations. The norm attention mechanism can be described as follows. The output is the normalization of the product of the query and key matrices, transposed, and the value matrix. Here, the query, key, and value matrices are all of the same dimensions, with n representing the sequence length and d, the feature dimension. We can transform this equation into a linear form, thanks to the properties of matrix multiplication. This linear form allows for recurrent prediction with a complexity of O, n times d squared, making it efficient during training relative to sequence length. Moreover, using linear attention ensures a constant computation complexity of O, d squared, regardless of sequence length, allowing for inference over unlimited long sequences. This is achieved by updating the product of the transposed key matrix and the value matrix recurrently, without the need for repeated computation of the entire attention matrix. However, when dealing with causal prediction tasks, the effectiveness of the right product is compromised, leading to the need for the computation of cumulative sum. This limitation hinders the potential for highly efficient parallel computation. As a result, we stick with the conventional left matrix multiplication in Lightning Attention-1. This is the motivation behind the introduction of Lightning Attention-2, specifically designed to address the challenges associated with the right product in such contexts. Lightning Attention-2 uses a tiling methodology throughout its entire computation process. Given the significant difference in memory bandwidth between HBM and SRAM within a GPU, Lightning Attention-2 applies a unique strategy for leveraging them. In each iteration, the query, key, and value matrices are segmented into blocks and then transferred to SRAM for computation. The operations within and between blocks are separated, with the former using the left product and the latter using the right product. This approach optimally exploits the computational and memory efficiencies associated with the right product, enhancing overall execution speed. During the forward pass of Lightning Attention-2, the output at time, t, can be formulated as the product of the query at time, t, and the sum of the product of the transposed key and value, both at time, s, where s is less than or equal to t. This equation can be rewritten in a recursive form. To perform tiling, we write the equations in block form. Given the total sequence length, n and block size, b, the matrices are divided into t, blocks of size b times d each. The output of the t plus 1, th block can be written in matrix form as the sum of the intra-block and interblock outputs. The complete expression of the forward pass of Lightning Attention-2 can be found in the algorithm provided. The intricate details of the Lightning Attention-2 implementation are explained through the forward pass and backward pass algorithms. These algorithms serve to encapsulate the nuanced computational procedures integral to Lightning Attention-2. Additionally, we provide a comprehensive derivation to facilitate a deeper understanding of Lightning Attention-2. The derivations are systematically presented for both the forward pass and the backward pass, contributing to a thorough understanding of the underlying mechanisms. Section Summary. In this section, the authors introduce Lightning Attention-2, a modified attention mechanism that optimizes computational efficiency. Lightning Attention-2 utilizes a tiling methodology and leverages the memory bandwidth between HBM and SRAM within a GPU. It employs a combination of left and right matrix products to enhance execution speed and memory efficiency. The authors provide a detailed explanation of the structural framework and computational procedures of Lightning Attention-2, including forward and backward passes. Section 3.2.2 Backward Pass. Let's delve into the backward pass, which is essentially the reverse process of the forward pass. We'll start with a given output derivative, denoted as do_t. From this, we can calculate the derivatives dq_t, dk_t, dv_t, and dkv_t. These derivatives are calculated using the output derivative and the transpose of kv_t, v_t, and k_t respectively. The derivative dkv_t is a bit more complex, as it involves a summation over all s greater than or equal to t, with each term being the product of lambda raised to the power st the transpose of Q underscore S, and do underscore S. We can express dkv underscore T recursively, starting with dkv underscore N plus 1, being 0, and dkv underscore T1, being the sum of lambda times dkv underscore T and the product of the transpose of Q underscore T1, and do underscore T1. To better understand this, let's consider these equations in a block style. We divide our total sequence length n into T blocks of size b, each containing elements of x, which can be q, k, v, o, or do. We start with dkv underscore T plus 1, being 0, and dkv underscore T being a summation over all s greater than tb, with each term being the product of lambda raised to the power stb, the transpose of Q underscore S, and do underscore S. For the T plus 1, th block, we calculate dq underscore tb plus r, using a complex formula involving lambda, v underscore s, k underscore s, do underscore tb plus r, and kv underscore tb. This formula can be broken down into two parts: the sum of products of lambda, v underscore s, k underscore s, and do underscore tb plus r, for s between tb plus 1 and tb plus r, and the product of lambda raised to the power r, do underscore tb plus r, and the transpose of kv underscore tb. In matrix form, we can express dq underscore T plus 1 as the sum of two terms: the intrablock term, which involves do underscore T plus 1, v underscore T plus 1, m, and k underscore T plus 1, and the interblock term, which involves lambda, do underscore T plus 1, and the transpose of kv underscore T. The recursion of dk underscore T steps from T plus 1 to T, and given kv underscore T plus 1, we can calculate dk underscore T for the TTH block using a similar complex formula involving v underscore T1, b plus r, lambda, do underscore S, Q underscore S, and dkv underscore T. This formula can also be broken down into two parts: the sum of products of v underscore T1, b plus r, lambda, do underscore S, and Q underscore S for S between T1, b plus r and tb, and the product of lambda raised to the power br, v underscore T1, b plus r, and the transpose of dkv underscore T. In matrix form, we can express dk underscore T1 as the sum of two terms: the intrablock term, which involves do underscore T1, v underscore T1, m, and Q underscore T1, and the interblock term, which involves lambda raised to the power b1, lambda caret minus 1, v underscore T1, and the transpose of dkv underscore T. Similarly, we can calculate dv underscore T for the TTH block using a complex formula involving k underscore T1, b plus r, lambda, Q underscore S, do underscore S, and dkv underscore T. This formula can also be broken down into two parts: the sum of products of k underscore T1, b plus r, lambda, Q underscore S, and do underscore S for S between T1, b plus r and tb, and the product of lambda raised to the power br, k underscore T1, b plus r, and dkv underscore T. In matrix form, we can express dv underscore T1 as the sum of two terms: the intrablock term, which involves Q underscore T1, k underscore T1, m, and do underscore T, and the interblock term, which involves lambda raised to the power b1, lambda caret minus 1, k underscore T1, and dkv underscore T. Finally, the recursive relation for dkv underscore T involves a summation over all s greater than tb, with each term being the product of lambda raised to the power stb, the transpose of Q underscore S, and do underscore S. This can be simplified to the sum of lambda raised to the power b times dkv underscore T plus 1, and the product of the transpose of lambda times Q underscore T and do underscore T. The backward pass of lightning Attention-2 is described in more detail in the algorithm. Section summary. In the backward pass, we compute the gradients for the query, key, and value vectors by recursively applying equations 11, 2, 20. These equations involve matrix operations and recursive relations to calculate the gradients for each block in the sequence. The algorithm provides a detailed description of the backward pass for lightning Attention-2. Section. Discussion. Let's talk about a recent method known as GLA, which models sequences using linear attention with data-dependent decay. This method uses a block parallel algorithm that works in chunks, using concepts of tiling and EO awareness. However, it differs from lightning attention-2 because it performs parallel computations for each block, which results in more memory usage. Another model, RetNet, is quite similar to Transnormer LLM and uses a chunkwise retention algorithm. This algorithm is similar to the forward pass of lightning attention-2 but doesn't take into account EO awareness or the backward pass. Now, let's move on to our experiments. We wanted to thoroughly evaluate the performance, speed, and memory usage of lightning attention-2. To do this, we conducted a series of tests on the Transnormer LLM model, which had lightning attention-2 integrated into it. We used the Metaseq framework, a PyTorch-based sequence modeling framework, for our implementation. All of our experiments were run on a GPU cluster with 128 A180G GPUs. We implemented the deployment of lightning attention-2 in Triton. We compared the speed and memory usage of 3 attention modules, lightning attention-1, lightning attention-2, and FLASHATTENTION2, all under a single A180G GPU. We found that the baseline runtime increased quadratically with the sequence length. However, lightning attention-2 performed much better, with its runtime increasing linearly. This difference in runtime became more noticeable as the sequence length increased. Our method also had a significant advantage in memory usage as the sequence length increased. We also evaluated the performance of the TRANSNORMERLLM 0.4b model under 2K contexts, comparing two versions, one with lightning attention-1 and the other with lightning attention-2. These experiments were conducted using 8 A180G GPUs. After 100,000 iterations, we found a small performance difference. The version with lightning attention-2 performed slightly worse than the one with lightning attention-1. We also compared the performance of several efficient large language models, including Llama FA2, TNL Louisiana 2, HGRN, and TNN. The TNL LA2 model performed slightly better than the other models. We also compared the training speeds of 3 versions: Transnormer LLM with lightning attention-2, TNL LA2, Transnormer LLM with lightning attention-1, TNL LA1, and Llama with flash attention-2, Llama FA2. We found that the TNL LA2 version had consistently high tokens per GPU per second during both the forward and backward passes, while the other two versions declined rapidly when the sequence length was increased from 1K to 92K. This suggests that lightning attention-2 is a significant improvement in handling unlimited sequence lengths in LLM. To evaluate the performance of lightning attention-2, we analyzed the TRANSNORMERLLM 15b model, which has 15 billion parameters. This model has 42 layers, 40 attention heads, and an overall embedding dimension of 5,120. It will be trained on a corpus of more than 1.3 trillion tokens with a sequence length of 6,144. The model achieved a processing speed of 1,620 tokens per GPU per second. We present the most recent results from the latest checkpoint for inclusion in the table. This evaluation was conducted using the LM Evaluation Harness Framework. Our benchmark focuses on 2 key areas: common sense reasoning, CSR, and multiple choice questions, MCQ. We also evaluated the Pythia 12b model under the same benchmarks. In all CSR tasks, the performance of TRANSNORMERLLM 15b was about 2% better than Pythia 12b. Furthermore, TRANSNORMERLLM 15b 100b showed an approximate 3.5% improvement over its 50 billion token stage, especially in the Hella Swag task, with over a 5% performance increase. Section Summary. The discussion section compares lightning attention-2 with other attention modules and evaluates its performance, speed, and memory utilization. It is shown that lightning attention-2 outperforms other modules in terms of runtime and memory usage, especially as the sequence length increases. The section also includes benchmarking results of lightning attention-2 in large language models, where it demonstrates superior performance in common sense reasoning tasks compared to other models. Section: Aggregated benchmarks. Summarized results. We're here to share the comprehensive results for two evaluation methods, MMLU and C-eval, under two different conditions, 0-shot and 5-shot. In the C-eval tasks, our model, TRANSNORMERLLM15B, outperformed Pythia 12B by approximately 2%. When we tested TRANSNORMERLLM15B in both Chinese, C-eval, and English, MMLU, under the 0-shot and 5-shot conditions, it surpassed the 25% baseline. This baseline represents the chance of randomly picking the correct answer in a 4-option scenario. However, we did observe some variability in the 5-shot multiple-choice question tasks, where the average score hovered around 26.5%,